Good evening to all. Today I am going to discuss about the differential amplifiers. In previous slide I posted about the BJT amplifier and FET amplifiers. So differential amplifier, it is nothing but it is an electronic device mainly used to amplify the difference between the two input voltage signals, and it is a main important in the integrated circuits of an analog system. So it typically forms an input stages of an operational amplifier, and in simple words, we can say that it is a device that amplifies the difference between the two input voltage signal, that is called as an differential amplifier. And then next, this is the main need of the differential amplifier is mainly it is used in physical measurements arises where the responses from the DC to many megahertz is required. So at that time we can utilize the differential amplifier as per the requirement, and it is also the basic input stage of the integrated amplifier circuit. And next, this is the block diagram of the differential amplifier. So we are applying two input signal as an voltage. So that is denoted as V1 and second is denoted as V2, and VD is nothing but differential voltage. So the difference between the two voltages denoted as VD, that is called as a differential amplifier. Finally, we are taking only one ended output, that is denoted as V0. So differential amplifier, it behaves as a subtractor circuit that basically subtracts the two input signal. So it can be constructed by using either BJT and also an FET. Next, so the output voltage is denoted by using the V1 and V2. So the output signal of a differential amplifier is proportional to the difference between the two input signal. So V0 is proportional to the V1 and V2. So here we know that V1 and V2 are the two input signals and V0 is single-ended output. So based on the input and output, the differential amplifier is classified into two types. One is common mode differential amplifier and second one differential mode differential amplifier. So based on the input signal, two modes are classified. So in this slide, we are going to discuss about the two modes and then configurations of the differential amplifier. And then next, basic configuration of differential amplifier. So this is the general configuration of the differential amplifier. So in differential amplifier, we are using two transistor stages. So we are applying two input signal. So therefore, we need two transistor stages. We are using only BJT type of transistor. So Q1 is one transistor and Q2 is denoted as second transistor. So we are applying source signal as VS1 and second source as VS2. So in base terminal, we are applying source resistor as the input, and we are applying signal at the base transistor of the Q1. And next from the Q2, we are applying the second voltage, that is denoted as VS2, and we are taking output as common in the collector terminal. So in BJT type of transistor, we are taking output only in the collector terminal. So the output for both the transistor is taken only at the collector terminal. It is common output. So that is denoted as V0, and supply is given to the collector terminal, that is denoted as plus VCC. And next one, the emitter terminal of the both the transistor is coupled. Here we have connected the emitter resistance and supply is denoted as minus VEE. This is the basic configurations of the differential amplifier. And first one, I'm going to discuss about the differential mode amplifier operation. So in case of differential mode operation, so first let us see the first case. So here I splitted the circuit into two parts. One is first Q1 transistor and second one Q2 transistor. So first I'm discussing about this Q1 transistor. So a signal is applied to the base of the transistor Q1 and no signal is applied at the base of the transistor Q2. And next one, here we are assuming that Q1 it acts as in the function may be present takes place in two ways. So one is first common emitter amplifier by which applied input at Q1 will produce or provide an amplified inverted signal at the output 1. And second one, we are taking the common collector amplifier in which the signal is appear at the emitter of Q1 and it is in phase with the input and slightly smaller than the Q1 of the transistor. so that the input signal of the Q1 that is in base, it drives the transistor. So that means at Q1 in on condition, the positive input signal will be takes place at the output signal of the Q1 transistor. So the voltage drop across the RC1 will be more, resulting the collector of the Q1 to be less positive. And next one, when the input signal is in negative, if you are applying input signal as negative, this is the negative signal, input signal. So at the time the transistor Q1 will get off. So therefore the resulting will be produced is very less voltage drop across the RC1. So it will cause the collector of Q1 to be more positive. In this way, an inverted output appears at the collector of Q1 by applying the signal at input 1. So at that time, so when Q1 gets on by positive half of the input, the current through RE will be increased. So already we know that in BJT I discussed about IE equal to IC. So in that way, here also we are going to assuming collector current is equal to emitter current. So therefore it is denoted as IC equal to IE. So the voltage drop across the RE, it will be more, thus causing the emitters of both the transistor, and it will be goes to the positive direction. So the current takes place only in the positive directions of the Q1 transistor. So this is the operation of the Q1 transistor. And next one, Q2 transistor. So at the time, this Q2 emitter is positive, will cause the Q2 to be negative. So at the time, Q2 is in off state condition. So the negative half cycle will be cause less current in the Q2. So resultantly, the voltage drop across the RC2 will be less than the collector terminal of the positive direction. So in this way, we will have a non-inverting output at the collector of Q2 for positive input at the base Q2 transistor. So this is the non-inverting output of the collector terminal present in the Q2 transistor. And next, suppose if the signal is now applied to the base of the transistor Q2, at the time the Q2 will be in grounded state. So in this condition, the case will be interchanged. So now Q2 will behave as an both common emitter and as well as the common collector amplifier, and Q1 will act as a common base amplifier. So at that time, Q2 will act as a CC configuration, and also common collector operation will be takes place in the Q2 transistor. Hence, the inverted amplified output will be received at the output of the Q1. At the output of Q2 will have a non-inverted amplifier result. So this is the non-inverted amplified result output of the transistor Q2. And next one, common mode amplifier. So in common mode amplifier, we are connecting supply voltage as common. So this is the difference between the common mode and the differential mode gain. So here, the transistor stages of Q1 and Q2, the base terminal is connected to the single supply voltage signal. So we are connecting both the base terminal from the transistors. It is given to the common supply voltage. So it is denoted as Vs1 is equal to Vs2. And next one, we are calculating the voltage level and then output voltage of the common mode. So in differential amplifier, the voltage generated at the output is proportional to the input of the signal. So this already I discussed in the definition of the differential amplifier. So when the two input signals are equal, that is, there are no phase shift difference between the two input signals. So therefore, the resulting of the output voltage will be in zero state. But practically, when the two input are similar in the differential amplifier, we are applying both the terminal as an input voltage are same. So at that time, the output, it does not exactly equal to zero. This is the main drawback of the common mode differential amplifier. So when we are applying similar voltage signal to the differential amplifier circuit, so the output does not exactly equal to the zero. So mostly in practical applications, we are using only the differential mode of amplifier. So the next CMRR. So CMRR is nothing but common mode rejection ratio. So now we are going to calculating the differential gain and common mode gain for the two modes. So the differential gain is calculated for the mode 1. So V naught is equal to AD into V1 minus V2, and AD is constant of proportionality, and it is nothing but gain of the differential amplifier. So AD equal to V naught by VD. So V naught is nothing but AD into V1 minus V2. VD is nothing but V1 minus V2. This is the difference of the two voltage signal. And next, common mode gain. So how we are calculating the common mode gain for the differential amplifier means by taking the two input signal of the average value. So by taking the average value of the two input signal, we are representing the gain of the common mode gain. So it is denoted as VC. So VC equal to V1 plus V2 divided by 2. So the average value of the two input signal is nothing but common mode gain. So in same way we are calculating the V naught for common mode signals. So hence the differential amplifier, it will produces the output voltage is proportional to the common mode signal. So it is denoted as V naught is equal to AC into VC. VC is nothing but average value of the common mode gain. AC is nothing but gain of the common mode amplifier. So therefore AC is equal to minus RC by RE. This is the AC value. And in this way, in this common mode signal, it exists an finite output for V1 is equal to V2 due to the common mode signal. And next one, by using the differential mode gain and then common mode gain, we are calculating entire total output of the differential amplifier. So the total output of the differential amplifier is given as V naught is equal to AD into VD plus AC into VC. So AD VD is nothing but differential gain, and AC VC is nothing but common mode gain. So by adding the two modes, we are getting the final V naught value for the differential amplifier. And next, common mode rejection ratio. So common mode CMRR is nothing but by using the ratio of AD and AC, we are calculating the CMRR value. So CMRR, it is the ratio of differential mode gain to the common mode gain is nothing but CMRR. So therefore CMRR is denoted as AD by AC. Here I represented the CMRR value in terms of decibels. So we are calculating in terms of decibels. So therefore CMRR equal to 20 log 10 modulus of AD by AC. This is the formula for CMRR in differential in common mode rejection ratio. And next, so the differential amplifier, it provides excellent bias stability because of the emitter current biasing. So the larger CMRR, it provides the better amplifier circuit of the differential gain. Next one, advantages of the differential amplifier. So these are all the few advantages. So first one, noise immunity. When we use a differential amplifier in the integrated circuits, it responds only to the different signal between the two input terminals, and it ignores the common mode signals. So due to the gain value is equal to 0 in common mode signal, we are normally utilizing only the differential amplifier circuits. And then drift immunity. So the major problem that arises in the amplifier circuit is the voltage level and as well as the effect of temperature. So due to the temperature, the changes may be occur in the differential amplifier. So it is denoted as a drift. So the changes occur slowly and it is denoted as drift. So it exhibits, it is mainly to eliminate the problem of drift. We are using the drift immunity. So the construction of differential amplifier is also used in all those circuits. So where low drift is very important. So such as stages of oscilloscopes and electronics voltmeter, we are using the differential amplifier construction. And next one, configurations of the amplifier. So based on the input level and output, we are configured the differential amplifier into four types. So first one, dual input balanced output, second one, dual input unbalanced output, third one, single input balanced output, and fourth one, single input unbalanced output. So next one, configurations diagram here I represented. So first configuration is dual input balance output. So dual input means for both the transistor we are connecting two supply sources. That is nothing but dual input. So it is denoted as VS1 and then VS2. So balanced output is nothing but at commonly we are taking for both the transistor we are taking output only in the collector terminal. So for both the transistor we are taking output in the collector terminal. It is balanced output. It is denoted as V0. So this connection is nothing but balanced output. And next second configuration, dual input and unbalanced output. So dual input is common and next unbalanced output is nothing but for only one transistor stage we are taking the output. This is nothing but unbalanced output. In transistor Q2 we are not taking the output. So any one of the transistor we are taking output. So that is denoted as the unbalanced output. So in the transistor stage at Q1 transistor we are taking output. And next slide. Next configuration. First one single input and then balanced output. So balanced output means we know that we are connecting output for both the transistor in collector terminal, but on input is we are applying only in the one transistor stages, that is Q1 transistor stage. So directly the Q2 transistor of the base terminal is goes to ground state. So this is nothing but single input. And next one in single input and unbalanced output. In same way, the Q2 transistor of the base terminal is given to the grounded state and we are applying input only in the single stage of the transistor, that is in Q1 transistor. So it is denoted as only one stage, that is voltage is nothing but VS1, and we are taking output in unbalanced output, that is we are taking output only in the Q1 transistor. So this stage is nothing but single input and then balanced output. So this is up to the main configurations of the differential amplifier, and next videos I am going to discuss about the tuned amplifiers. Thank you.